start the session.
Just give me a second. Okay, you can hear me, right?
Yeah.
Okay. Hi everyone. I'm Benjamin, and I'm going to present camera model in computer vision for you. And thank you very much for having me in your class. And also, whenever you have any question, feel free to interrupt me and ask me. In the middle of the session, we'll have a break, and yeah, that's it. Okay, so this, uh, my camera is on, right? Is my camera on? Uh, I assume my camera is on.
Yeah.
I'm not sure.
Go.
Okay, okay, okay. So, uh, pinhole camera and perspective projection. So let's talk about that. What is a pinhole camera? A pinhole camera models a camera as a point in the 3D space. So consider a 3D space and assume we have a camera in this 3D space. Uh, this camera can have some coordinate in the space, right? Depending on which origin we choose in this 3D space and which axis. So it has some 3D coordinate. However, camera might be big, right? So it has some volume. But let's assume that the camera is a point only, just one point, and that point can be the camera lens, for example. We call that point optical center. And when we consider the camera as a point in the 3D space, then that's called pinhole camera. In other words, the lens of camera is considered as a 3D point located in the 3D space. Then now consider some object in the 3D space, right? It's a 3D object. And when it passes through the camera, what happens? So assume we have the image plane here, or negative, for example, in your camera. Then this object passes through your camera lens and then will be projected onto this image plane, right? And this image plane is a 2D image. Uh, and also, as you see, this object, for this projected onto the negative or the image plane, it needs to be flipped twice. So once in this direction, then once in this direction, if you see my hand. Also, the distance between the camera lens and the negative or the image plane is focal length. We denote it by F. Okay. So as I told you in the previous image, in the previous figure that I showed you, for this projection, we need to flip the image twice. In order to make it easier and not to, we can change the model in this way. We assume that the negative or the image plane is between the camera lens and the object. If we do that, then the image will not need to be flipped twice to be projected onto the image plane. For example, consider this 3D object, and this is the lens of the camera, right? So I have brought the frame from here to here, right? Then also assume that, so the camera itself and the object, they are in the 3D space, right? Therefore, I have three axes, X, Y, Z, right? Also, the image itself, the image plane for the negative, right, is 2D, right? It is 2D. Therefore, I can denote the axes of this 2D image plane by U and V. Then what do we? Okay, so here the Y here, for example, is showing the height of my object, right? correspondingly, I have some height of my object in the 2D plane, and that's V, because V here shows the height here. And U kind of shows the X, but we don't have any Z on the image plane. Agreed? Okay. And this is the focal length. So the focal length is the distance between the image plane and the lens, the camera. Also, we have Z. What is that? The distance of the coordinate of the or the depth of the object, 3D object, from the origin in the 3D space. Agreed. Here, I'm assuming that my camera is on the origin here. Camera lens is at the origin in the 3D space. Okay. Any questions so far? Just as I said, I can't
Yeah.
see. Yes, yes.
So like in this case, the vector u and the v should be perpendicular, right?
Yeah, yes, exactly. Because these are the basis vectors in
Okay.
the 3D,
Sure.
in the 2D. So the basis vectors are orthogonal to each other, right? Or perpendicular.
Oh yeah, sure.
Okay. So yeah, please feel free to interrupt me whenever you have any question, because I can't see you. So when you don't ask question, I assume that you have understood. So okay, so here this is a figure that we had in the previous slide. Now, according to the intercept theorem or Thales's theorem, we learned that in high school or even middle school. According to the Thales's theorem or intercept theorem, what happens? We have this. Let me consider this triangle. So it becomes like a triangle, right? So this is V, this is Y, this is F, and this is Z. Okay. Then do you agree that we have this? This is Thales theorem or intercept theorem. V over Y equals F over Z, right? We learned that in geometry. Then likewise, we have it for X. U over X equals F over Z, okay? So we have these two from Thales theorem. Then let's rearrange the terms. So for example, these multiply the sides by X. Then you will have these. Also for the second equation, multiply the sides by Y, then you will get this. Okay. These equations, these are called perspective projection of the 3D object by the camera onto the image plane. Okay. Why? What is it doing? So it's kind of saying that, so X and Y and Z are the 3D coordinates of the object. Using these equations, we can map them to U and V in the image plane, right? So therefore, we call it perspective projection. And in these equations, X, Y, and Z, and also U and V are all in millimeters, right? Millimeters. So because they have to have the same unit here. But it's easier for us to represent U and V in terms of pixels, because we are in image plane and we are in the image. Usually we work with pixels rather than millimeters, right? Therefore, for this, we divide F by S in these two equations. If you have these S terms, then U and V become like in terms of pixels, while X and Y and Z are in terms of millimeters. What is S? S is the millimeter size of every pixel. So every pixel, how many millimeters is every pixel away from its neighbor pixel, right? So, I mean, what is the distance between every two pixels, every two adjacent pixels? So every pixel is S millimeters, and obviously it depends on the resolution of the image, right? So here, by having S in the equations, we could just have U and V in terms of pixels. Okay. Another thing which we need to say, that we assume that the origin of in the image plane is on the corner, top left corner. But if so, yeah, the origin is on the top left corner of image. we can translate the origin of the image to be the middle of the image, right here, right? Assume that the coordinate of the middle of the image is OU and OV, is denoted by OU and OV if origin is the top left corner. Then if I add plus OU plus OV to these equations, then I'm assuming that the origin is in the middle of the image. Okay. So far we have had these two equations. Agreed? Okay. Now, now multiply the sides of these two equations by z. So we'll have these zu equals f over s x plus ou z. Also, zv equals f over sy plus ovz, right? Now I'm here, rather than z, I'm replacing z's with lambdas, and I tell you why. So we have replaced the scale z with an arbitrary z as a scalar. Okay. What is the reason behind that? This is intuitively because we can state a line passing through 2 points x1 and x2 as this. What do I mean? Consider these 2 points in this space. How can I represent the line between them? Can you tell me? Any suggestions? How can I represent the points connecting the points between x1 and x2 on the line between x1 and x2?
Is it like for x2, suppose x1, x2 are two vectors, so x would be x2 minus x1.
So x2 minus x1 is this vector, exact, right? This is x2 minus x1. That's correct. This is this vector. So x2 minus x1 is the vector connecting x1 to x2. But I'm saying that, how can I represent the points on this vector? Of course, do you agree that I can say lambda times x2 minus x1, lambda times it, where lambda is between 0 and 1? Then by sweeping lambda between 0 and 1, I will have any point here. So when lambda is 0, then, but by the way, I need to have x1 plus this. So starting from x1 plus this vector, right? When lambda is 0, it becomes x1. When lambda is 1, it becomes x2. When lambda is between 0 and 1, it's between these 2 points. Now, how can I go beyond the points? Can you tell me? Either over x2 or over x1. Can you give me your suggestion?
Increasing or decreasing lambda.
Exactly. That's right. Thank you. So if lambda is between minus infinity and infinite, there is no range between for lambda, then I can go cover the whole line where x1 and x2 are on the line. Okay. So intuitively, that's the reason. Here, z is showing the depth, right? So I by sweeping lambda, I can have various depths, right? We can also have negative depth. If what does it mean? Negative depth means that I'm behind the camera, right? So that's the intuitive reason. Now consider these two equations that we just discussed. We derived that step by step, right? Then I can write it as a system of linear equations. Do you agree that these two equations 7 and 8 are equivalent to equation 9? Let me tell you why. So this is lambda u lambda v, right? Equals this. And what is this? Let's write it. So this times this, right? So f over sx plus 0 times y plus ouz, and then this times this becomes 0x plus f over sy plus ovz, right? And so this must be equal to the first row, and this must be equal to the second row, which is exactly the equation 7 and 8. Right? Okay. Now, in camera model for computer vision, we usually add a fake dimensionality to be able to go back and forth between scaling and not scaling by a scale lambda. So I want to go back and forth between scaling and not scaling. There, we use a technique. That's a technique in computer vision that they do that a lot. So consider this vector u. By the way, when I denote the vector by bold small case and scalars by not bold small case. So u, the vector u has assume its elements are u and v, two-dimensional. Then I add a fake dimensionality. I make it three-dimensional, and I put 1, for example, here. This is called the coordinates in the Cartesian coordinates. This is Cartesian coordinates. This, after adding the fake dimensionality, is called homogeneous coordinate. Okay, this is this definition. Okay, and usually we denote the homogeneous coordinates by tilde above the vector. Okay, so for example, x can be 3D, right? X, y, z, and x tilde then becomes x, y, z, and 1, right? A fake dimensionality. You will see why this fake dimensionality is useful. For example, a use case is here in equation 12. Consider lambda u tilde, right? Then it becomes lambda uv1, right? Then it is equal to lambda u, lambda v, lambda. Agree? I can go now. So this I can using this lambda and also this homogeneous coordinate. I can go back to my Cartesian coordinate, my original Cartesian coordinate. How? If I divide all of the coordinates, all of the elements by the last element, for example, by the last element which was supposed to be the fake dimensionality. So lambda u over lambda becomes u. Lambda v over lambda, which is the fake dimensionality, becomes v. And this is exactly our original Cartesian coordinate, right? So we can go back and forth between Cartesian coordinate and homogeneous coordinate. Okay.
Sorry.
Yes.
So is the fake dimension only like, is it only, does it only have a span of 1, or can you have?
No, exactly. That's a good question. This fake dimensionality can be any scalar. For example, here is
Okay.
lambda, right? Here is lambda, for example.
Okay.
So
Thank
if
you.
you consider this only, the fake dimensionality is 1. If you consider this, the fake dimensionality is lambda.
Okay,
Right?
got it. Yeah.
Okay.
So Benjamin, maybe not
Yes.
bad. Go to the previous slide. Oh, you
Which
will talk about that. So slide number 7. So because I haven't went through for example, affine transformation, and you will talk that this is kind of affine transformation matrix.
Well, we will talk
Okay.
about the
Okay,
transformations,
sure. Yeah,
including the
sure.
affine one. Yeah, we'll see that in this lecture. Okay. So do you remember the perspective projection which we saw in equation 9? It was this, right? If you don't remember, let me go back to equation 9 for you to remember. This was equation 9, just right? We derived that. And so I'm repeating it here. Now let's state it in homogeneous coordinates. So these are Cartesian coordinates. Let's represent them or state them in homogeneous coordinates. So u and v, I replace it by u and v and 1. Also x, y, and z by x, y, and z and 1, right? But I need to modify this because the dimensionality of the matrix multiplications should match each other. For example, here it is this matrix is 2 by 3, and this is 3 by 1, And this is also 2 by 1. So 2 by 3 times 3 by 1 becomes 2 by 1, correct. This became 3 by 1. This is 4 by 1. Therefore, this needs to be 3 by 4. As a result, I need to add this row and this column in a way that still this I can these equations hold true. So you can see that these two are equivalent. Let me tell you why. Consider this. What is this added column doing? 0, 0, 0, almost nothing, right? So because everything multiplied by 0 becomes 0, so it does nothing, and you will get these two equations exactly that you have. This one, why am I adding that? Here, I will have lambda times 1. I want lambda to become equal to z. Therefore, I put 1 here, and lambda times 1 becomes this times this, which is z, right? So 0, 0 times x plus 0 times y plus 1 times z plus 0 times 1, which is z. Exactly here, right? What you might be wondering, why don't I put all zeros here? If I do that, then lambda becomes 0, right? Because lambda will be equal to 0. And if lambda is equal to 0, I will have division by 0, and it gives me a problem, right? That's the reason I want lambda to be equal, for example, to something like z. And that now you understand why I replaced that z there in equation 7 and 8 by lambda. Because I want lambda to become like z, right? Equal to z. Did you understand how I changed these Cartesian coordinates to homogeneous coordinates in these equations? Is it clear for you, guys? Also, why do you understand this equation? So if you multiply this matrix by this matrix, as we learned in high school, you will get this three-dimensional vector, right? So this equals this. Therefore, the first element is lambda u, right? Lambda u equals the first row. Then the second element, lambda v, equals the second row. Then the third element, lambda 1, lambda times 1, equals z, the third row, z. Okay? Now we replace lambda with what we found here. Lambda equals z. Therefore, z times u is this, right? Let me first rearrange this by dividing the sides by lambda. If I do that, do you agree that I will get this? Let me clean this a bit because it became too occupied, too busy. Okay, so here we have this, right? I divide the sides by lambda, so I will get this. Now I know that lambda equals z, so I replace lambda with z. Agreed? These two cancel each other, becomes 1, so I will get this. Likewise, consider this equation, divide the sides by lambda. You will get this. According to this equation, lambda equals z, so I replace lambda with z. I will get this. These two are equal to each other, becomes 1, therefore I get this. Agreed?
Benjamin, one of
And
the students has a question.
yeah, just don't need to ask me. Just interrupt me whenever you have any question. Don't need to raise hand. Okay. Yes.
A little bit question about the equation 13. So I'd like to know
Yes.
why we add the 1 in the fourth row and the third column. Why it's over there?
Why do we have add 1 here? Because I want to make the Cartesian coordinate homogeneous coordinate.
No. For the
This one.
for the left one, yeah. Where is
This one, because I want is what do you want me to put here? If you want me to put 0 here, do you agree that lambda becomes 0? Because
no? It
if
should
I
not be
put
0.
yeah, so it shouldn't, because I don't want to have division by 0, right? So I should put something. You can put something, some other scalar. The easiest one is 1. You can put 2. You can put 3, right? Then if you put 2, for example, lambda becomes 2z. You understand?
Okay, is it like for keeping the z? So the z would be the constant, right?
Yeah, I'm saying that it must be some scalar, and the easiest one is 1.
Okay.
Exactly.
Yeah.
Yeah. So, and also I did that because I wanted lambda to become equal to z. This is usually we do that in computer vision. And okay, now if the camera lens optical sent, by the way, again, as I said, interrupt me. Don't need to raise hand if you have any question. If the camera lens or optical center is not exactly on the origin of the 3D space, so far we assume that it is on the origin, right? Now, in general, it might not be on the origin of the 3D space. And also its axis might not be aligned with the axis of the 3D space. So it might have both rotation and translation, right? If it is not on the origin, it has translation. If its axis is not aligned with the axes of the 3D space, then it also has rotation. So we need to correct its position by rotation and translation. Usually in image processing and computer vision, when we have both rotation and translation, we usually call it an affine transformation. Okay. So here, then what should we do? So x, y, z, we apply some rotation. This is rotation matrix, right? Which is 3 by 3 because we are in the 3D space. Also, this is translation vector. So it's also a 3-dimensional vector because we are in the 3D space, right? So we denote this rotation matrix by R. By the way, bold capital letter in my slides are usually for matrix, right? So R, and this is the XYZ, and also the vector T, right? I denote this after rotation. I denote the 3D coordinates after rotation and translation by X prime, Z, Y prime, and Z prime, okay? X, Y, Z are before rotation and translation. So now, do you agree that I can write this as this? By making XYZ homogeneous, by having 1 here at the end, I can bring the vector of translation vector inside the next to the rotation matrix as the 4th column. And now I think you see one of the benefits of having homogeneous coordinates, because now we could combine the rotation matrix and translation vector into one matrix, right? So if we do that, then you will get this. So here, this part is R. We put it next to the vector T. Agreed? Okay. This also can be stated in homogeneous coordinates. So far X, Y, and Z became homogeneous. We can also make X prime, Y prime, Z prime homogeneous by adding effect dimensionality at its end, right? However, if I do that, then this becomes a 4x1 vector. Therefore, I need to change the dimensionalities of these matrices too, because here it was 3x1. The whole thing was 3x4, and this was 4x1, so it would make sense mathematically. But now it became 4x1, therefore this is also 4x1, therefore this must be 4x4, right? This was 3x4, we need to make it 4x4, therefore we need to add a fake row. So we add the fake row as the last, because this is added as a last dimension, right? And I add 0, 0, 0, 1. Why? Because I want 1 to be equal to 1, right? Then, as you see, I have R matrix here. I have T vector here. I have 0 vector transpose. Why? Why does it, as you see, it's bold 0. It means that 0 vector, the vector of 0. And it's transpose because usually in science, when we say vector, we consider vectors as column vectors. Okay, and this is a row vector, so we say 0 transpose. And this is a scalar 1, right? And I repeat this too. Agreed so far? Okay. In 3D, we can have various type of rotations, right? So do you agree that in 2D, we only have one type of rotation, either clockwise or counterclockwise, right? So in 2D, the rotation matrix, I don't know if you have seen or not, it's cosine theta minus sine theta, cosine theta. This is a formula for rotation in the 2D. So if you multiply this by x and y, gives you x prime, y prime, rotated point. So x and y is a point in this 2D plane, 2D space. You can rotate it around the origin by this, and theta is the angle. You can have, based on the theta that you choose, you can have clockwise or counterclockwise rotation, right? So, but now what about the 3D? In 3D, we can have rotation around x-axis, rotation around y-axis, rotation around z-axis. And if we have a mixture of rotations, because we can have rotations around both x and y, then you can decompose it into two rotations. So first around x and then around y. Or if we have a mixture of rotations around all three axes, then we can decompose it into three rotations, right? One by one. So rotation around x-axis, for rotation around any axis, you need to make that axis kind of fixed, and the other way, the other two should have rotation. So for example, here x, the first coordinate, right? So the first column and the first row are both fixed, and we put one here, and the rest has a rotation like in 2D, right? In y-axis, we fix the second row and column, and the rest I have cosine minus sine, sine, cosine. For z, I fix the third row and column, and I have this sine and cosine and sine again for the other two axes. These three rotations are named pitch, yaw, and roll. So pitch basically means nose up and down. See my face. Hopefully my camera is working. If you can't see my face, let me know. Pitch is so I can rotate my head in three ways. One way is this. Right. This is pitch. So nose up and down. Or I can rotate my head like this. Right. This is yaw. Nose moves from side to side. The other way that I can rotate my head is roll, which is this. Right? This is roll. Ears up and down, right? Ears up and down. So, and as you see, it's a circular, clockwise or counterclockwise movement of the body as it moves forward. So you can have pitch, roll, and yaw for example, an airplane. Consider this. So when the airplane is like, if you see my hands, is like this, goes like this, it's roll, right? If it goes like this, its nose goes up and down, I believe, yeah, it's pitch. Then it can also be like this. It can be rotated like this, exactly the way that I can rotate my chair. This is yaw, right? And in control theory, controlling
Pardon, I have
the
a question.
yes.
Yeah, it depends on us that consider the clockwise positive or counterclockwise or not. There is a constant, for example, the clockwise would be positive and the counterclockwise would be negative.
So what was the question? I didn't get it. So
Uh,
you're saying that
I wanted to know that the clockwise would be positive
Oh yeah, so it's again with I think this is by convention. You can choose anything,
Uh-huh.
but in my opinion, usually let me think.
Okay.
If we consider one of them as positive, the other one is negative. But if you're asking which one is positive and which one is negative, I should think. We should
Uh-huh.
think. One way to figure it out, you can have positive theta or negative theta in these equations and see how you have rotation, and for example visualize it, and you will find out whether positive rotation is this side clockwise or counterclockwise. I don't have them on my mind. I haven't memorized them, but I can say that in my opinion this is not that much important because
Uh-huh.
it's just humans convention. It's just humans convention.
Okay.
Yeah.
Okay.
I
Thank you so much.
No problem. Maybe if we go to, for example, monkeys convention or animals conventions, they see that as the other way around. So that's why I'm saying this is humans convention. That's the reason that it's not that much important. So
But I believe this is just clockwise. So if we rotate
clockwise,
something
okay, yeah.
20 degrees, it will go
Mhm.
clockwise. Yeah.
Okay. So
Uh-huh.
in control theory, it's very important to control these rotations, especially for aerodynamics, which are very important. For example, if it is an airplane for passengers, then you shouldn't have too much roll, right? But if it is uh, it's a aircraft for war, for example, then I mean the jets, then we can have a lot of freedom for roll, right? So they can control how much that object can move and have rotation. So you can have control over these things. If, yes, and you can give freedom for how much rotation you can have. Let's move on, and so equation 13 can be stated for a rotated and translated camera location. So recall equation 13. This is equation 13, right? What was that? The coordinate here were x, y, and z in one. Homogeneous coordinates for x, y, and z. But now this was assuming that the camera is on the origin. There is no translation and no rotation of camera. But what if I have rotation and translation? Then I replace x, y, and z in one with x prime, y prime, z prime, and one. Homogeneous coordinates for after translation and coordination and rotation. All right. So I have this. Now, do you agree that I can, what was that? This itself was this. So it was applying rotation and translation on x, y, and z, right? According to equation 17, I believe. Equation 17, right? So we have equation 22. So I can replace this with this, and I'll have it. Do you agree that I can simplify it further? How? I have these zeros. I also have these. Let's see the dimensionalities. What was that? This was 4 by 1. This was 3 by 4. This is 3 by 1. Right. What about this one? This is 3 by 1. This is 3 by 4. This is 4 by 4. This is 4 by 1, which makes sense. But here, 4 by 4, consider these two 4s. I can reduce them to 3 by 3. So it's to 3. So it can be, sorry about that. It can become 3 by 3, then 3 by 4. Exactly, this is what I have done here. So 3 by 3, and this is 3 by 4. This is 4 by 1. So this becomes 3 by 1 as before. But we have got rid of these this column and this row, right? This is exactly what I have done. So I simplified it. So this is exactly what we have found. I'm repeating that. Let's analyze that. Without, okay, let me go back to the previous slide. Without reading the next slide, can you tell me what is the interpretation of equation 23? Can you give me suggestions? Anyone? What is it doing? Can you hear my voice?
Just gonna take a guess here, but
Yeah.
your first matrix, I guess that one is for image motion, and then the second matrix is for like rotation and translation. So like rotating and translating images in the plane.
Yeah, your guess is very close to the correct answer. Thank you. So what is this? This is 3D coordinate of object, 3D object, right? In the 3D space. What is this? 2D coordinate or 2D pixel in image plane, right? So this is basically mapping 3D coordinates of the object to 2D coordinate in the image in terms of pixel, right? How does it do that? First, what does this step do? It maps the 3D coordinate of the object to the coordinate of the camera, 3D to 3D coordinate of camera. What does this step do? Maps 3D coordinate in camera to 2D coordinate in image or negative of the camera. Did you understand? So we have two steps. First, we need to map the 3D coordinate of object to the 3D coordinate of camera. Then we need to map the 3D coordinate of camera to the 2D coordinate of the negative of the camera. Right? That's very interesting, I believe. By the way, because of these S's, I know that U and V are in terms of pixels. Now, the parameters f over s, f was the focal length, s was that, do you remember? It was the for having the pixels. OU and OV are the coordinates of the center of the image in the negative. These 3 or 4 parameters are called intrinsic parameters of the camera. Okay, and therefore, we name this matrix which has these parameters, we name that intrinsic characteristics matrix, and we denote it by K. Okay, we had this matrix here. This is K, right? Now, the parameters of rotation and translation, Rij, and also Tx, Ty, Tz, they are called extrinsic parameters of the camera because they are not inside the camera. It's outside of the camera. It depends on where we locate the camera in the 3D space. They are called extrinsic parameters of the camera. So this matrix R and T contains the extrinsic parameters. And yes, so the following matrix, this matrix. So what is this? This is K, extrinsic parameters. These are the intrinsic parameters. Multiplication of K and R and T, we call it mapping matrix. We denote it by M, M standing for mapping. Why? Because basically this is exactly what we saw here in this equation. This is M. What is it doing? It maps 3D coordinate of the object to 2D pixel coordinate in the negative of the camera, right? So this is a mapping matrix. It maps that. Okay. Any questions so far?
So, sorry, go ahead.
Oh, you can go first.
Okay, so the translation part here, so will it always center the image to the camera, like to the lens itself, or is the translation part, like, what is the translation part exactly doing?
So here, why do we have this translation and rotation? If the if you assume that you are in the 3D space, right? If you assume that the origin the camera is on the origin, because origin is in your hand, right? Where do you assume the origin is? If you assume that the camera is on the origin, and also you assume that the axes of the camera are the axes of the 3D space, the basis vectors of this 3D space, then you don't have any rotation and translation. Then any object has 3D space, right?
Okay.
Then you can get rid of this rotation and translation matrix, because that's the 3D coordinate of the objects with respect to camera. However, what if you put origin and the axis in some other place where they are not on the camera? Then you need to have rotation and translation for transforming the 3D coordinate of the object to the 3D coordinate of the space of the camera, right? Because camera is not on the origin anymore.
Not on the origin, yeah. Okay,
So
I understand. Thank you.
Benjamin, can we say, for example, if let's say I have my laptop here, and if I, for example, rotate my laptop, so this is installation of my camera. So I can, with this translation, I can make the image somehow upright based on the, for example, installation, and change the images. So, and then when you see the image, you see the upright image rather than the rotated image.
Completely understand, because I can't see you and completely. Can you repeat what you mean?
That's fine. So let's other student ask a question.
Okay, sorry, I didn't understand. And someone else had question, right?
I believe
No?
so, but
Okay.
yeah, but go ahead. Yeah.
By the way, when anyone, whenever you ask me question, please be descriptive, because I need to imagine it. I can't see you. It's a hard experience. So explain with details so I can understand what your question. Otherwise, it's hard for me to imagine. So camera calibration. Now finding the parameters in the mapping matrix is called camera calibration. What do I mean? This was the mapping matrix, right? This has some parameters: F, S, OU, OV, these rotation values, translation values, all of these. If we want to find these, this is called camera calibration. It means that we calibrate the camera, right? And this is a 3x3 matrix. This is 3x4 matrix. This becomes a 3x4 matrix, right? Therefore, I can write the elements of the mapping matrix as Mij, where I goes from 1 to 3 and j goes from 1 to 4, right? Then, so now do you agree that if I use equation 23, so the mapping thing equation, the famous mapping equation that we had, so it becomes lambda times uv1, also this mapping matrix M, this, right? So I want to find the M values, the elements of this mapping matrix. This is called camera calibration. Okay, now consider a pair of actual point x1, y1, z1, and a corresponding image point u1, v1. What do I mean? By the way, for transpose means that I want to consider these vectors as column vectors. So what do I mean by this? A pair of actual point and corresponding image point. Do you agree that whatever point I have in the 3D space, it has some corresponding pixel in the image plane? Agreed? So consider one 3D point, x1, y1, z1, right? z1 is the depth of that point. Then it has some coordinate in the image plane, u1, v1. Okay, consider this. Now let's put these in equation 27. What do I get? So lambda u1, right, equals this times this, which is this, right? What about lambda v? It's this times this. It's this. Lambda v1. By the way, here x, y, and z are replaced with x1, y1, and z1 because I have put these in this equation, right? Likewise, lambda times 1, lambda is this times this. Agreed? Okay. I have these three. I have repeated them here. Now, lambda is this, right? Lambda is found. So we can replace lambdas here with this third equation. Then I will get these two equations. Agreed? So for every pair of actual point, 3D point, and its corresponding pixel, right? I can get two equations, right? What are my unknowns? All of these mij's. So how many unknowns do I have? 3 by 4, 12. I have 12 unknowns, right? All of these elements. For every pair, I can find two equations. How many equations do I need to have a linear system of equations and find the unknowns? So I have 12 unknowns. Therefore, I need 12 equations. Every pair gives me two equations. How many pairs do I need? As a result, I need 6 pairs, right? So if I get 6 pairs of actual points and their corresponding image points, I can calibrate the camera. Did you understand what I mean? So basically, I choose 6 pairs in the 3D space. I found where they are in the image. Then I can calibrate my camera. I need to take that image by my camera, right? Then don't rotate and translate my camera anymore. Then I can calibrate that camera. By the way,
So
it's
it could
how.
be with chessboard or something
Yes,
like
yes,
that, right?
exactly. Yes, I'm
Yeah,
gonna show a figure of
yeah,
chessboard.
sure.
Yeah.
So all of them is about you have one camera, for example, installed somewhere, and you
Yeah.
don't have camera, let's say, uh, properties, then with one chessboard, image of one chessboard that your camera taken, and finding corresponding pixels, then you can find your, for example, camera characteristic.
So basically, what do they do in practice? So if I can find, so for example, they put some chessboard on the 3D space somewhere. They usually install it. So because why? They don't. You can move your camera, right? You can also, the 3D object can move. For example, this chessboard can move, but they usually fix one of them to become easier. So usually they install the chessboard, or it might be a small chessboard, doesn't matter, somewhere in the corner of somewhere, right? And then you have your camera, you install your camera, so you can play around with your camera, rotate it and translate it. And then you take a picture of that chessboard. Then you know the 3D locations of the corners of the chessboard. So the 3D objects are already known to you. You know where they are. Now the only thing is that you need to find them in the image, captured image. For example, you can use Harris corner detection. You can use corner detection algorithms to find those corners, right? There are techniques in computer vision for doing that, such as Harris corner detection or edge detection, whatever. You find those corners in the image, and then you have the pairs. You take 6 of them, 6 pairs, and then you calibrate your camera. Did you understand? So these are some figures that they use of chessboards, right? For example, what have they done here? This is a captured image, and they have applied corner detection on them. And here, these are the pixels UV, right? U and V for this point. And we know where it is in the 3D space, so we can calibrate it. Okay. So how do we,
So the
yes.
sorry, the calibration process itself, it's done by like a human being, I guess, in that we have to find the 6 pairs and then make sure that they correspond to the right image points, like the image
You
points
can,
and the axle points.
so the question is whether we need to do it manually or we can automate it. I believe we can automate it, as I said. For example, if you install the 3D object like chessboard in the same place always. So X, Y, Z is already known to you. It doesn't change, right? You don't move that object. You only calculate X, Y, Z of that once, okay? Then you also can find the corners, corresponding corners by algorithms, corner detection algorithms. You don't need to find them manually. You can, for example, you might go, so this is the image, sorry, this is the image that you have. Let me zoom. This is the image that you have, and then you can go to your device and click on that and see which pixel it is, how many rows I should go and how many columns, what is the coordinate of the pixel. You can do it manually, but they usually do it automatically by corner detection. Why do you do it manually? Did you get it? Did I answer your
Yeah,
question?
I think so. Thanks.
Okay. So we have these equations. So as I said, we have these. By the way, let's rearrange these two equations into an. So if I bring these to the other side, then I will get these two equations. I rearrange them. Now, do you agree that I can have a system of linear equations? So my unknowns are these, all of these, right? This is a column vector, M11 to M34, and I have a matrix of coefficients, and all of the coefficients in this matrix are known. So let's see what are the elements of these. So it is a 12 by 12 matrix because I have 12 unknowns. So odd and even rows are these. So these are odd rows and these are even rows. Why do I do this? So for every pair, I have 2 rows of A for every pair. So consider one of the pairs, for example, that like this. Then what happens? What is the coefficient of M11? This is x1, which is known, right? Which is known, a known value, xy. Xi means for the first pair it becomes x1, right? Then y1 for M12, so y1, z1, right? Then for the next thing is M14. For M14, its coefficient is 1. What about M21, M22, and M23? Here, their coefficients are 0. Also M24, their coefficients are 0 in this equation. What about the rest? So for M31, its coefficient is minus x1. Minus x1 u1. Minus x1 u1. What about M32? Its coefficient is minus y1 u1. Likewise. So for example, M34, its coefficient is minus u1. If you also consider the coefficients in the second equation, you will get the coefficients in the even rows of A, right? And you will have pairs. So we will have x1, y1, z1, x2, y2, z2, and also u1, u1, v1, u2, v2, etc. You have 6. I goes from 1 to 6, right? So the coefficients in A are known, and you have matrix A times this vector equals the 0 matrix, because this is 12 by 12. This is 12 by 1, so 12 by 1. So the whole thing becomes 12 by 1. So this is a vector of 12 by 1, 0 vector, right? How do we solve this system of linear equations? I believe we learned it either in high school, the last years of high school, or the calculus in the first years of undergrad. So it was one of the techniques is Cramer's rule. You can use various techniques to solve a system of linear equations. One of them is Cramer's rule, right? There are various ways. If you see any linear algebra course, they explain these techniques. Okay, or you can give it to MATLAB or any library to solve it for you. Okay, so now our unknown M11 to M34 are known, so we calibrated our camera. Agreed? Now, finding intrinsic and extrinsic characteristics, method 1. So now we want to find the elements of F over S, OU, OV, and rotation values and translation values individually, separately. So in the camera calibration, recall that we learned all of the M values, and the M values are the matrix multiplication of this matrix and this matrix. But what if I know the value of F over S, or R11, or TX, or OU? Then how can we find those? In other words, I want to find the intrinsic and extrinsic parameters rather than the parameters of the mapping matrix. So the method 1, we have two methods at least for that, assumes that the mapping matrix is already known. It means that we already have done the camera calibration, right? If we do that, then so the matrix M is known. Then now let's multiply this matrix with this matrix. So the matrix M becomes equal to this. Okay. Then what happens? So we know that this is equal to this. We already know this matrix by camera calibration, right? Mij elements are already calculated by camera calibration. Now we can find out how these, each of these. Let's see how. We define Q1 as this. So consider this. I define it as Q1. By the way, this transpose Q1, this is Q1 is a vector, and this as Q2, and this as Q3. Okay. Also, by the way, this method 1 is good assuming that the points are not noisy. What do I mean by not noisy? I mean that my camera has worked perfectly, and also I don't have any noise in my measurement of XYZ and also its pixel. So my my corner detection algorithm works perfectly, my camera works perfectly, my ruler in the 3D space works perfectly, I don't have any noise. Then I can use this technique. Why should I have make this assumption? There is one reason for that. Because if I don't have any noise, then the rotation matrix can be assumed to be orthonormal. Orthonormality or orthogonality of the rotation matrix is one of the properties of the rotation matrix. Okay. So what was the rotation matrix? This was the rotation matrix, right? When it is orthogonal, it means that this vector R11, R12, and R13 transpose. Also this vector R21, R22, R23. Also this vector R31, R32, and R33 are orthogonal, and also each of them has unit length. Okay. So if that's the case, then L2 norm of R3 is 1. According to the definition of L2 norm, this is definition of L2 norm. R3J squared summation, where J goes from 1 to 3 is 1. So the size to the power of 2, it gives us this. Then, so I have this equation. I'm going to use this equation. Okay. Keep this in mind. Also, we know that R1 and R3 are orthogonal to each other. Therefore, their inner product becomes 0. And this is the inner product, right? R1J times R3J, where J goes from 1 to 3. Right? I'm going to use this equation too. So keep these two equations in mind. Okay. Now consider, so this was what we had, and these are Q1, Q2, and Q3 that we defined. Now consider Q1 transpose Q3. By the way, we know Q1, Q2, and Q3 because Mij's values are known, right? So Q1 transpose Q3 becomes some known scalar, right? Now, what is Q1? So this is Q1. What is Q3? This is Q3. So multiply the elements together, you will get this. Summation of F over S1 R1J plus R3J OU times R3J, where J goes from 1 to 3. Summation, this is the inner product. Now what happens? I have R1J here and one R3J. We know that R1J and R3J, if you multiply them over the dimensions, becomes 0. Why? Because exactly because of this. Equation 33, right? So this term goes away. Then I will have OU R3J squared, right? And I know that I can bring OU behind the summation. I know that summation of R3J squared is 1, according to this equation, equation 32, right? So it becomes OU, OU times 1, OU. So I have this equation, OU equals this. Likewise, Q2 transpose Q3. What happens? This is Q2, and this is Q3, right? If you have inner product, you will get this. Likewise, R2j, R3j, when you multiply them and sum over the dimensions, it becomes 0 because they are orthogonal. Then you will have R3j squared, OV comes out of the summation. You will have OV times 1. Therefore, OV equals this. As you, what do you want to find? We wanted to find OU, OV, F over S, T, R, right? All of these. OU is found. OV is found. Okay, now let's find the other one. So Q1 transpose Q1. So this vector its inner product by itself. So you will have this to the power of 2, right? Or these elements to the power of 2 summation. Then what do I do here? Here I use the binomial theorem equation. A plus b squared is a squared plus b squared plus 2ab, right? If I do that, the first element squared plus the second element squared plus 2 the first times the second one. Agreed? Okay. Now we know that this becomes 0 over the summation because of equation 33. Because of equation 33. So this goes away. This also over when I have summation becomes 1. This also becomes 1. Right? So I will have f over s squared times 1 plus OU squared times 1. Right? Interestingly, so let's read. So this equals this, right? Rearrange it, and also I have the power of 2, so I will have a square root from the side. So I'll get this. Interestingly, we had found OU here in equation 34. Replace OU with what we have found, you will get this. We know all of these values, and this is equal to f over s. So f over s is also found. Therefore, we found OU, we found OV, we found f over s. As a result, in this slide, we found the intrinsic parameters, intrinsic characteristics of the camera. Now let's find the extrinsic characteristics. How? Consider, so here, we know that, just give me a second to think. Yes, TZ equals M34. M34 is known, so TZ is found. Now what about this one, M14? So this one equals M14, right? This equals M14. Rearrange the terms, you will get this. Okay. Now we already found f over s in equation 36. In equation 36, we found f over s. Therefore, we know s over f, which is its reciprocal, right? Also, we know OU from the previous slide, so we know everything here. So Tx is found. We can likewise, we can do it for Ty. This equals M24. Rearrange the terms, you will get this. We know S over F and OV from previous slide, so you know this. Therefore, Ty is found. As a result, we found Tz, we found Tx, we found Ty, so the translation values are found, which are the extrinsic parameters, right?
So when you could
Yeah.
you go to slide 23?
Yeah.
Yeah. We may have one question in the quiz from this slide, so it's it just want help to find if you have that question, you may find the answer from here. Thank you, Vinny.
Yes. So, is there any question among the students, among you guys, about from this slide? Because as Morteza said, apparently you have a quiz about it. Did you fully understand this slide? Okay. Now, method 2. So, there's another way to find the intrinsic and extrinsic characteristics. This method, for this method, by the way, we can have noise. We don't need to make an assumption that it's not noisy. So this method uses alternative optimization. What is alternative optimization? This is an optimization technique which says that if I have several optimization variables, I can assume that one of them is fixed. For example, I have two optimization variables. I assume one of them is fixed. I optimize over the other one, And then in the next iteration, I assume that the other one is fixed and I optimize over the first one. So I do it iteratively, right? So I alternate between optimizing over each of them, right? This is called alternative optimization. Its idea is similar to the idea of Gibbs sampling, if you have heard of this in statistics. Okay. So what do we do here? So this method first considers some valid random values for intrinsic parameters, right? K, matrix K. Then based on that, it finds the parameters of R and T, the extrinsic parameters. Then next time, it assumes that extrinsic parameters are fixed. Then it fine tunes the intrinsic parameters. Then after finding the intrinsic parameters, it fine tunes the extrinsic parameters again. It does that iteratively. Okay, let's see. Consider a pair of actual point, x1, y1, z1, and corresponding image point, u1, v1. Okay, so let's use the famous mapping equation that we saw. This we had k, we had rotation and translation. The whole thing was the mapping matrix, right? Here, what do we do now? So this k is a pain in the neck. Left, in order to get rid of that, left multiply the sides by k inverse, because we know k inverse k becomes identity, so it goes away. So here it goes away, but I will have k in, so lambda 1 k inverse this, right? Now I denote k inverse times this vector denoted by u1 prime, v1 prime, and 1. So this. Okay. So this becomes u1 prime, v1 prime, and 1. And as the rest is the same as here, but this k went away, right? Then you tell me, so consider this equation. What do we have? We know that, just give me a second. Yes. This times this becomes lambda 1 u1 prime. Don't you agree? So consider this is lambda 1. Lambda 1 u1 prime equals this times this, which is this. But why is lambda prime this? Because of the third equation. Lambda 1 times 1 equals this times this, right? I'm just doing the simple matrix multiplication. Then, so I will have three equations where I'm replacing lambda 1 in the two first equations. Then I will get these two equations. This is lambda 1. Agreed? So what happens? I have these two equations, right? And so every pair, x1, y1, z1, and u1, v1, right? Every pair that we had, here we had a pair, right? Gives me two equations, right? How many unknowns do I have? So these are unknowns, right? Rotation values and translation values. So 12 unknowns, right? So I have 12 unknowns and two equations per pair of points. Therefore, I need 6 pairs here again. Okay. So by these equations, again, so as you see, ideas are repeated, but used in different situations. Here again, previously we needed 6 pairs for camera calibration. Here we need 6 pairs for finding the translation and rotation values, right? So again, I can have a system of linear equations where the unknowns are rotation values and translation values, right? And the odd and even rows of the A are found based on this, right? I goes from 1 to 6, and then I can solve it using Cramer's rule, right? Agreed? Any questions so far? Is everything clear? Okay. So after calculating the extrinsic parameters, we update the intrinsic parameters. Do you remember what did I tell you? We are doing alternative optimization. We assume that we know the we know that here we assume that K is known, right, by random values initialized by random values, by valid random values, I mean. When we found the rotation and translation, now we need to fine tune K again, right? After calculating the extrinsic parameters, translation and rotation, we need to update the intrinsic parameters K, right? So let's do that. So this is the famous mapping formula that we had, right? Then, do you agree that so this is known now. Now this is known in this iteration, right? We just found it in the previous iteration. Therefore, I can define this times this. I define it by x1 prime, y1 prime, z1 prime. This is 3 by 4. This is 4 by 1, so this must be 3 by 1. So I replace this part with this. Agreed? Okay. Now, what do I have? So I have a system of linear equations. So I know according to the third equation, lambda times 1 equals this times this. So it's lambda equals z1 prime, right? What about the other two equations? I have this and also this. Lambda u1 equals this times this, which is this. Also lambda v1 equals this times this, right? Rearrange. So I mean, what do I mean by rearranging? Divide the sides by lambda. We also know that lambda equals z1 prime, so I will get these two, right? So we got these two. We got these two. And here, what are my unknowns? You tell me. F over S, OU, and OV. Agreed? These were the unknowns, right? So I have two equations. How many unknowns do I have? These, right? So you can see 3 unknowns because we usually consider F over S as one unknown. Doesn't matter. Or 3 or 2 to 4. Usually we say 3 unknowns. And every pair gave us 2 equations. As a result, we need 2 pairs. 2 pairs are required to solve this linear of system of equation, right? Then, so again, we can have a system of linear equations, A times these 3 unknowns, where I have odd and even rows. So A is 4 by 3. Write this, and we can solve this equation, system of linear equation. You might be wondering that when we have 3 unknowns, we need 3 equations, right? Therefore, you can either ignore one of the rows of A. So to make it 3 by 3, what do I mean by ignoring? I mean consider one pair and one equation from the second pair. If you do that, then A becomes 3 by 3. This is one technique. The other one is that you consider 2 system of linear equations. We can divide these 4 equations into 3 equations, right? 2 sets of 3 equations. Then each of them gives you some solution. Then take the average solution, the average of solution. You can do that too. Again, you for solving the system of linear equations, you use Cramer's rule. Did you understand? I think we can have a break now. So if you agree, let's have a 15-minute break and come back at 8:40.
Sure, Benjamin. I will stop the recording, and I have my PC on the lab.
Okay, so let me share screen again. Okay, so any question before we continue?
Yeah, I just have a quick question about the intrinsic versus extrinsic parameters. So are the extrinsic parameters only related to the rotation, and the intrinsic is more to do with like the distance from the camera to the image?
No, the extrinsic parameters are just for rotation and translation of camera.
Yeah, okay.
And intrinsic parameters are for the parameters inside the camera. What do I mean? The focal length,
Oh,
the
okay.
the resolution. The focal length is f. The resolution is s, right? And also the origin of the image or origin of the negative, OU and OV.
So the intrinsic parameters are kind of inherent to the type of camera?
Yeah, exactly. They are inside the camera. But extrinsic parameters are not inside the camera. It depends on where you put the camera.
Yeah, okay, that makes sense.
Okay,
Thank you.
then no problem. Any other question? No? Okay, let's continue. Depth inference from images. So when we have several images, using several images, probably with different perspectives and even with different cameras, right? So either they can be different images with taken from the same camera but with different perspectives, or you might have two different cameras or several different cameras and take some image from the same scene. Okay, it must be from the same scene. Then we can infer the 3D coordinates of the scene. It's very interesting, right? So what do I mean? By a bunch of 2D images from some 3D object, you can find out the coordinates of that 3D object. It's like a miracle. It's like a magic. So you have a bunch of 2D images. You can infer the 3D coordinate of that object. Okay, how do we do that? Assume we have K images. Yes.
Is this something I don't really know something about like the Google open source the media pipe? So that will be some kind of.
What is that?
Something? Is there open source library called the media pipe? So is this something related to some like using the 2D image to get the interpreted 3D dimension, 3D interpretation?
Okay. So maybe I'm not sure what that is, but there are other techniques to do that. So there are some recent methods in deep learning. They are called NERF, I guess. As far as I remember, it was NERF, right? If you Google NERF, you will see that it's a family of methods. There are thousands of papers on NERF. So what do? They learn they learn a lot of depth images from the scene, and then they have in the test phase, using just even a single 2D image, they can infer the 3D object of that. So for example, you give it a 2D view of some chair, it can give you behind the chair too. So it gives you a 3D scene. It can infer that. So those are other techniques. I'm not sure what you said is using NERF or not. Here, I'm using the basic fundamental computer vision for inferring the depth using 2D images. It's not using deep learning. Okay. Okay. Any other question? So by the way, what I'm gonna explain here exactly explains why we can infer the 3D object and depth of this world using our eyes, because each of our eyes is like a camera. We have two cameras, and then we can infer the depth. If one of our eyes is blind, then we can't infer the depth. I don't know if you have tried this or not. Put your hand on one of your eyes and then ask your friend to bring the pen back and forth and try to grab that pen. After some time, you might not find out exactly where the pen is because you can't infer the depth using one eye. You might do it by chance, but you are doing it just by chance. You can't find out the depth with one eye. You need two eyes to infer the depth. Okay, that's interesting. Okay, so assume we have K images taken by either one camera or K different cameras. Then so we have K mapping matrices, right? Assume we have pairs of actual points x, y, z and corresponding image points u1, v1, u2, v2, and uk, vk, right? Of K images. So here I have one actual point, and for each actual point x, y, z, I have K UI VIs. I have k pixel points in the k different images, right? So let's put these pairs in the famous mapping equation that we had. So we have k equations like this. The unknown variables are x, y, z of that object, right? While ui, vi, where I goes from 1 to k, and also the mapping matrices are known, right? Then what do we do? So now consider these, consider one of these, for example, equations. Then do you agree that lambda 1 u1 equals that first row of the m1 times x, right? Times the whole column x, y, z1. This is exactly what I have written here. Lambda I ui for the ith image is m1 1 I x, m1 2 iy, etc. Right? Where I stands for index of the which image, okay, image. Also, lambda 1 times 1 is the last row of m1 times the whole thing. So it's this, right? Therefore, I can replace lambda I with this equation. Then I will get this equation. Likewise, I can write it for lambda 1 v1, lambda 1 v1. I will get this, and I can replace lambda I with this equation, then to get this equation. Agreed? So, therefore, every image pair, right? And what do I mean? Every pair. So every pair of actual point and its corresponding pixel in the image, every image actually provides two equations. We just saw that, right? For the ith image, I got these two equations. Okay. How many unknowns do I have? You tell me. X, Y, Z, right? X, Y, Z. So because of 3D object. So how many pairs? So every image provides two equations. I have three unknowns. Therefore, two images are enough. Two images are, or two cameras, or only two images are enough for inferring the 3D space. Now, if you put these equations in a system of linear equations, right, then you can solve it using Cramer's rule, for example. By the way, it's an overdetermined system of linear equations because it's it's 4 by 3, but this is 3 unknowns only. So again, as I said, you can either ignore one of the rows, or you can make it, you will have several solutions, and then you take the average between them. Okay, and you can use Cramer's rule. Now, can you tell me why are two eyes in our human's body enough for inferring 3D space? We just explained that. For inferring three unknowns, for finding three unknowns, we need two images. Each image gives us two equations. Therefore, we need two images. Therefore, we need two cameras in our body, two eyes. If our space was 5D, 5-dimensional, in order to understand the depth in that 5-dimensional, everything in that 5-dimensional, we needed three eyes. But as we are in the 3D space, we need two eyes to understand it. Do you understand? Interesting. Okay. By the way, for people whose eyes are not straight, this is also an important thing for you to understand. For example, one of the eyes is looking this way, one of the eyes is looking this way. I don't know what's the word in English for that. Okay, so some people, their eyes are not straight, right? Therefore, this eye, for example, sees this region. This eye also sees this region, right? For those people, they can only understand the depth of the overlap of the two eyes. Therefore, if there is some object here in this place where the other eye can't see, then that person can't find out what's the depth of that object. Okay. Only where they have the overlap, it can find out the depth. Okay. Now, depth inference from images. So let's continue that. Do you agree that if I want to use this technique, of course, if I have one point, then I can using two pixels in the two images, I can find out its depth. But if I want to find out the depth x, y, z, the 3D object, the 3D coordinate of all points in the scene, what should I do? I should do this calculation for all of the points. If I have 1000 points in this 3D space, I have to solve 1000 system of linear equations. So it's very time consuming, right? If I have p pixels, I need to do it p times. So it's in its order of complexity is OP, where O is a big O notation, right? Therefore, there are some more some other techniques which have accelerated that for finding the depth of the whole scene. Rather than two images, do you agree that rather than two images from the two cameras, we can use a projector emitting light on the scene and a camera taking an image frame from the scene? So rather than having two cameras to capture the scene, let one of the cameras be the projector, which is the opposite of camera. It emits light, and the other one camera. So we have a projector emitting light and a camera getting the light from that scene. Then using a camera and a projector, we also can find the depth of the 3D points. This is a technique used using a structured light. So it uses a structured light, which improves the time complexity of depth calculation. It was proposed in 2003 by Skarstein and Selesky in reference to. These are important people in computer vision. This method uses structured light images, which are similar to Haar wavelets. I don't know if you have seen Haar wavelets. Haar wavelets are like this. Let me add a page. Sorry, I need to go with faster pace for us to cover everything here. So Haar wavelets are like this, and with different frequencies. Like these are Haar wavelets. And they are used a lot in computer vision, especially. Why is it? Because wavelets are like sine and cosine, the regular wavelets. But Haar wavelets are like this, and they are suitable for digital images, right? And they have been used also for face detection, face feature detection in computer vision. For example, see the Viola Jones face detector. It uses Haar wavelets. Okay. So what does it do? So it gives us these structured images like this. So once it projects light like this, so the bottom part of the image is dark. The top part is bright. And for another time, it does it the other way around. So we'll have two images, right? And as you see, it's like Haar wavelets. Then what does it do? It gets the subtraction of image 1 minus image 2. Do you agree that where in this subtracted image, if I have positive value, it means that it is in top part, right? Because it is in image 1. If I get a negative value, it means that it is in the bottom part. Then it fine tunes that by making this pattern finer. It was coarse, makes it finer. So it does that. It halves the parts every time, and does that iteratively, right? Then in using some technique, I'm not going to explain the details of that technique. I'm just giving you a hint. You can go and read that, the details of that. We can find the depth of every pixel in the time O log of p rather than OP. So we improve the time complexity from OP to O log of p, where p is a number of pixels in the image, right? So time became logarithmic. Okay, now planar scenes. Camera on top of the scene with known distance. What do I mean? So consider a camera which is looking at a planar scene, where the scene is a plane on the plane. Why is it useful? Have you seen that in industry? Have you seen the use cases of this in industry? Can you give me some guesses? Have you seen convey?
Yeah,
Yes.
detection of faulty parts in manufacturing of automobile parts.
Yes, maybe. So whenever you by the way, you said that checking things on the automobile parts, but I'm saying that the scene must be planar, okay? But automobile parts might not be planar. So assume this is a camera looking at the scene, and this is automobile. I don't know. automobile parts. But this is not planar. This is curvy, right? What I mean is that it's a plane, but it's used a lot, especially in industry when we have a conveyor. Have you seen the conveyors where objects move on the conveyor? For example, there are boxes on the right. If the distance of the camera from the conveyor is significant, then the height of objects can be negligible. Therefore, you can see that you can assume that the conveyor is a planar scene. So you see that in industry a lot, right? Okay. We can assume that the scene is on the XY plane. So do you agree that I can choose my origin and my axis in the 3D space? Let me assume that this planar scene is on the XY axis. And I assume it's Z, therefore is 0, right? Because it's on the XY axis, right? And also assume that distance of camera from the scene is D. Okay. Now consider that famous equation of mapping. What do we have here? So TZ is D. Do you agree? Because TX, TY, TZ is a translation of camera, right? And we know that camera has distance D from the origin, right? In terms of Z. So TZ is D. Also, let me think. Z of the scene, so this is the scene, right? This is the scene. Its Z is 0 because it's on the plane, on the XY plane. Okay. Then what happens? Let's see what happens. Give me a second to think. Okay, I can simplify this further. How? By the way, these also become 0. These R's. Why? Because my scene is now in a 2D. It's on a plane. It's not a 3D scene, right? Therefore, these become 0, and I am only on XY plane. Therefore, the Z thing part becomes 0. This is exactly the rotation, do you remember, for around the Z axis. Then what happens? Then as I have this column, and also this became 0, this times this cancel each other. So I can, this 3x4 matrix can be simplified to 3x3. Also, this 4x1 vector becomes 3x1, right? So I simplified that. Then also, do you agree? This is 1, this is D. In terms of, if you do the matrix multiplication, you can bring D here. These are exactly equal to each other. If you do the matrix multiplication, you can see that they are equal to each other. I brought D here. Okay. Now I have this matrix. Okay. This matrix, is it known? Assume that we know the camera's intrinsic characteristics, K. So we know how to calculate them. We saw them in the previous slides, right? So F over S is known, OU and OV are known. So I know this matrix. Also D in this case, I'm assuming that distance is known. In the next case, I will relax this assumption. But now I assume that the height of camera is known. So D is also known. Therefore, this matrix is completely known. I denote it by K prime. Why not K? Because in K, this is 1. This is not D. Okay. Now, so I replace this matrix with the K prime that I just defined. Then what happens? Just give me a second. Yes. Then I will have this. Agreed? So this K prime is a pain in the neck. Then what should we do? Left multiply the size by K prime inverse to get rid of that. Therefore, I will have K prime inverse here. This K prime goes away, becomes identity. And the rest as before. Now I have this term. UV are the pixels in the conveyor or on the plane. And this is also known. I define this as U prime V prime 1 because K prime is known. So K prime inverse is known. Also, this K prime inverse times UV1, I define it by U prime V prime 1. So I replace this with U prime V prime 1. Also have lambda here. And I have this as before. Now, do you agree that if you solve this linear system of equation, lambda times 1 equals what? This last row times this. 0 times x plus 0 times 1 plus 1 times 1. Therefore, lambda equals 1. Right? So, do you agree that lambda equals 1? Now, let's go back from homogeneous coordinates to Cartesian coordinates. So, we had u prime v prime 1. This is the fake dimensionality. We can bring it back to u prime v prime by dividing the side by lambda, right? So if we do that, as lambda is 1 also, if you solve this system of linear equation, you will end up with these two equations, right? Basically, it means that multiply this side by x and y. Also, tx and ty is multiplied by 1. So plus tx and ty. Okay? What is this? It's very interesting. We came completely from 3D to 2D. This became 2D. This is rotation and translation in 2D, right? Because our scene was planar. It reduced to 2D affine transformation. It to only transformation, translation and rotation. And we know that in 2D in XY plane, the rotation with angle theta is this. It's cosine theta minus sine theta, cosine theta. XY plus TX, TY. Agreed? So what is it doing? It is mapping the coordinates xy of the planar scene to u prime v prime, the pixels in the negative of the camera, or the image of the camera, frame of the camera. So this is what we found. This is called Euclidean transformation, also called the rigid transformation. Okay. The object might be rotated and or translated on the xy plane. By the way, I think you understand me that when I say so, because initially in the course, in the lecture, I said that's for translation and rotation of the camera. Here I'm saying that it's for translation and rotation of the objects on the conveyor or on the plane. Does it matter? Doesn't matter, because if you rotate camera, it's like that you assume the camera is fixed and you rotate the scene. They are the two sides of the same coin. Do you understand what I'm saying? So it's the same thing. And how many unknowns do we have? We have theta, rotation angle, tx and ty, the translation. Okay. So we have these three unknowns, and we know that every pair of actual point in 2D plane and also its corresponding image pixel uv, how many equations do they give us? Every pair gives me two equations, as in this equation 53. So every pair gives me two equations. How many unknowns do I have? I have three unknowns. As a result, two pairs are sufficient for me to find the unknowns to solve this system of linear equations. Agreed? Now, what if the distance or the height of the camera from the planar scene is not known? Let's relax that assumption. Let's go back to our famous mapping equation, right? This time I have my D is unknown, so I don't bring it inside K. Do you remember the last time I brought it inside K because K was known, also D was known. I wanted all the known things to become in one place. Now D is unknown, so I don't bring it inside K. Now this is not K prime anymore, this is K. But this K is still a pain in the neck. Let's get rid of that. Left multiply the sides by K inverse. Then I will have K inverse here. Also, this becomes identity. Sorry, here. Sorry, this becomes identity here. I define this K inverse UV1 as U prime V prime 1. Okay. Then I will get this. And this has become identity here. So D, now D is a pain in the neck, which is unknown. Let's divide the sides by D. divide the sides of this equation by d. So I have lambda over d. Also, all of these elements divided by d. But here, this d becomes 1. Agreed? Now let's solve this. Consider the last row. Lambda d times 1 equals this last row times this. Therefore, lambda over d equals 1. Therefore, lambda equals 1. Lambda over d is 1. Therefore, lambda is 1. D. Lambda is d. So now, if you set lambda to d and solve this system of linear equation, you will get this. So this system of linear equations simplifies to 2 equations. Agreed? Then what happens? So again, I went back from homogeneous coordinates to Cartesian coordinate. Then I can factor out 1 over d, because I have 1 over d in all of the elements, so I can factor it out. Also here, I have 1 over d, so I factor it out. Right? Again, it's the same, similar to before. I only have 1 over d multiplied to the terms of the equation. This is rotation matrix. This is translation vector, right? This is rotation in the xy plane. Interesting. Now, this is the equation that we had. This time, I have 4 unknowns. So theta and tx and ty and d, all of them are unknown. So I have 4 unknowns, and every pair of actual point on the planar scene and corresponding image pixel gives me 2 equations. Therefore, again, 2 pairs are sufficient for me to find the unknown variables in this system of linear equations. Agreed? Any questions so far? No? So now projective transform, also called homography. Now assume that a camera views a planar scene but from an arbitrary viewpoint. So now, do you remember, so far I assumed that the camera was looking at the planar scene from top, perpendicularly looking, right? But now I relax that assumption and I assume that my scene is like planar still, but I can look at it from some angle, with some angle. I put the camera, see my hand, I put it like this, right? Then what happens? So again, I assume that the scene is on the xy plane, so z is 0. So consider the famous mapping equation. I set z to 0 because my scene is planar, assuming on the xy plane. And this time, as I have 0 here, what happened? By the way, this time my tz is not equal to a constant d. It's not, because this time I'm looking at it from some angle, right? Then what happens? Because of this 0, this column goes away, because this column is multiplied by 0, becomes 0. So this 3 by 4 matrix becomes 3 by 3, and this 4 by 1 vector becomes 3 by 1. Now I define this matrix K times this matrix. I define it by phi. So it's a 3 by 3 matrix. Okay, therefore I can replace this by phi. I will have this. And this phi is called projective transform, also called homography. Okay, so consider this equation 56. It gives me 3 equations. It's a system of linear equations, right? And I can replace lambdas here with what I found here. As a result, it gives me actually 2 equations. So every pair of actual point and corresponding image pixel provides 2 equations, right? How many unknowns do I have here in my projective transform? I have 9 unknowns, 3 by 3, right? So I have 9 unknowns. Every pair gives me 2 equations. Therefore, we need 4 pairs of points to find 5. And it can be solved using any technique such as Cramer's rule. Okay. Again, still assume that we are in the plane, the scene is planar, but now who said that the rotation matrix should be only that sine cosine thing? The rotation matrix can be relaxed to be any matrix without any condition. This is called affine transformation, which is a transformation such as rotation or something else of points followed by a possible translation. Okay. Clear so far? So in these few last slides, I talked about some transformations where the scene is assumed to be planar, and I said that they are very useful, especially in industry. Now let's talk about panorama images. Have you heard of panorama images? Can you hear me, by the way?
Yeah, we can hear
Okay,
you.
Yeah.
okay, great. So now panorama images, it is becoming cooler. Okay, panorama images, what are they? Are made of multiple images which have overlap, and we put them together so they reconstruct a wide range of scene altogether. For example, have you seen some? You can go and Google it, so you can see the desert, for example, with 360 degrees of view. So you can go to all different parts of the desert and see all parts of the sky and the desert. How do they do that? They can't take it by one camera, right? They should either, for example, they face the camera to this scene, they take a picture, then they move the camera a little bit, then they take the picture again, then move camera a little bit, take the picture, and so the pictures have some overlap with each other, right? And then they stitch the images together, so we'll have a wide range image, right? So this is panorama image. But let's see its theory. So far we were taking pairs. So far we were taking pairs of actual points and corresponding image pixel, right? But for panorama images, we take pairs of image pixels in one image and corresponding image pixel in another image. So rather than having pairs of actual 3D or 2D point in the space scene and the corresponding pixel, let's consider two corresponding pixels in two different images, but from the same thing. For example, I have a same 3D coordinate in this scene, or 2D coordinate, 3D coordinate in the scene, doesn't matter. Do you agree that this scene has two corresponding pixels in two different images when the images have overlap, right? So now my pairs are the corresponding pixels in across images. We assume that in panorama images, we assume that the scene is planar, which is justified. Why? Why is this assumption justified? Because either the scene is actually planar, such as the conveyor in industry, or the scene is very far away from the camera. So it becomes like a plane. When it is very far away, the heights and valleys, the mountains, everything, they become negligible. They become like a plane, right? And now we understand that that is why most panorama images are from nature scenes, like deserts or the skies or very far away mountains. This is the reason. The scene must be assumed to be planar, which is far away from the camera. Okay. Therefore, we can use projective transformation or homography for the panorama images. So what was homography? We just introduced that in previous slides. Now consider two images which have overlap. So these two equations I have, right? And xy is the actual point in the planar scene which is shared between the two images, right? Which is in the overlap of the two images, right? So I use the same xy here. Now consider the first equation here. So this is a pain in the neck, right? Phi. So left multiply the sides by phi inverse. As a result, xy1, this becomes identity, xy1 becomes lambda 1 phi inverse u1 v11. Agreed? Okay, now consider the second equation. Lambda 2 U2 V21 equals phi2 xy1, but xy1 itself was equal to this, so I replace xy1 by this, so I'll get this and this, right? What is it doing? It's basically mapping u1 and v1 to u2 and v2, so it's a map between the pixels of two images using phi1 and phi2. It's very interesting. So you can see which, so by the way, we need to find phi1 and phi2 using pairs. So when you have overlap, you just need to take several pairs, as we discussed for homography in previous slide. We just take several corresponding pixels, and the other corresponding pixels are found automatically using this equation, using this mapping. In this way, we can simply stitch the images together so they become a wide range image. Did you understand? It's very cool, right? Now, finding corresponding pixels in two images from the same scene. So this time I have two, for example, cameras. So by the way, this might be related to panorama images, but now this time I don't want to stitch them. I just want to find the map between two cameras. Okay, this time, in this time, not just for the panorama images, and not in this section. Now I don't assume that the scene is planar. For panorama, I was assuming that.
Sorry.
Yes.
So are the intrinsic parameters of both of these cameras equal or are different?
No. So in panorama, you mean? In which one?
No. In this one, the next
in
one.
this
Yeah.
section?
Yeah.
No. They can be
No?
different.
Okay.
Yes. We'll see that. So consider two cameras, left camera and right camera. They're denoted by CL and CR, left camera and right camera. I have a 3D object X, right? X, Y, Z. And but this means that it's a vector, right? And each of them has some negative or frame, right? Each of these cameras. So U is the pixel coordinate corresponding to this 3D object X. Consider X connect X to the lens of the camera, left camera. So it gives you this ray, right? We call it optical ray for left camera. Also, consider any point on the optical ray of left camera. Excuse me. And connect every point on this optical ray to the lens of the right camera, like this. It gives you optical rays for right camera. Agreed? And all of these optical rays of right camera and optical ray of left camera lie on some plane, right? They are on some plane. We call it epipolar plane. This plane. And also, when these optical rays of right camera intersect this frame of the right camera, it gives us some line or ray some line in the frame of right camera. We call it right epipolar line. Okay. Now connect the left camera and right camera together by some line. They intersect the frames of left and right cameras. We call them left epipole and right epipole. Okay. So we have two cameras taking some picture image from the same scene. Okay. The goal is finding corresponding pixels in the two images from the same scene. First, assume that the cameras, for now, we will relax this assumption. We assume that the cameras are normalized and their intrinsic matrices are identity matrix. So not only we assume for now that their intrinsic matrices are equal, but also we assume that their identity. So it means basically the cameras are normalized. Okay, here subscripts L and R stand for left and right cameras or images respectively. Okay. Now, again, suppose that the left camera is on the origin of the 3D space. I can choose the origin of 3D space. I assume the left camera is on that without any rotation. So the axis of the 3D space is aligned with the axis of the left camera. Therefore, RL, rotation of left camera, is identity, and its translation vector is 0. Right. Now let's go back to our famous mapping equation. So we had this K, R, T, right? I'm considering that for the left camera. So it's lambda L, U, L, V, L, 1. So these are the pixels in the left image, in the frame of the left camera. KL, intrinsic matrix for the left camera. RL, TL, rotation and translation of left camera. XYZ, XYZ is the scene, right? Now, according to equation 59, my assumption KL is identity. Also, I assumed that my RL is identity and TL is 0. So, because I can choose my 3D axis. Therefore, this becomes very simple. So, multiply this by the elements of these. So you will have lambda L UL, lambda L U VL, and lambda L equals. So this 0 is multiplied by 1. So 0 and 1 goes away because everything multiplied by 0 becomes 0 except infinity. Then I will have these multiplied by 1. So I will have this. Okay. Now consider the famous mapping equation for the right camera. So according to our assumption in equation 59, its intrinsic matrix is identity. However, its rotation matrix and translation vector, we don't know it yet. So we put R, R, and TR, right? Then I have X, Y, Z, and 1 here. I found X, Y, and Z in equation 60. So I replace X, Y, and Z with lambda L, UL, lambda L, VL, and lambda L. Right. I have one here at the end. I'll put the 1 here also. What else do we do here? These lambda L's I can factor out, right? So I factor it out. By the way, let me clean this part. It's a bit busy. We know that RR is multiplied by these 3 and TR is multiplied by this, right? Therefore, TR times 1 is plus TR, right? RR times these, I can factor out the scalar lambda L. Lambda L is factored out, RR times this. And this is repeated here. So far clear? If you have any question, ask me. So I have this. We just found it, right? Now I can denote it by UR tilde, right? Because it's a homogeneous coordinates. Also, I can denote this by UL tilde. So this is the pixels in the frame of right camera. This is the pixels in the frame of left camera. UR tilde and UL tilde. Right? Okay. Let me clean this part. Now, see what I do. Just give me a second. What happened? Sorry about that. Okay. I left multiply the sides by TR, but using outer product. You know outer product, right? With inner product. We also have outer product. Outer product of two vectors is another vector. Inner product of two vectors is a scalar. And also, we know that when we have two vectors like these, their outer product is perpendicular to the plane containing those two vectors, right? You know that, right? So I'm using outer product, TR outer product. So I have TR outer product of this term, then TR outer product of this term, then TR outer product of this term, right? Why do I do that? Because I want to get rid of this. We know that the outer product of every vector with itself becomes 0, right? The outer product of every vector with itself becomes 0. So so this goes away. This becomes 0. Then I have lambda r. It's a scalar, so I can bring it out in the multiplication. Then I have TR outer product UR tilde. Also I have lambda L, which is a scalar. I can bring it out. TR outer product RR UL tilde. Then I left multiply the sides by UR tilde transpose. Basically, I mean have an inner product of the sides by UR. UR tilde transpose. This means the inner product between UR tilde and this, right? Inner. If you don't know what inner and outer products are, just Google them. You can find their Wikipedia pages. It's easy, nothing complicated. Okay, so you have UR tilde transpose on the sides. Why do I do that? Because this term is a pain in the neck. I want to get rid of that, and I know that the result of this must be perpendicular to UR tilde. Do you agree? Because this is TR outer product UR tilde. I know that TR anything outer product by UR tilde is perpendicular to the UR tilde. If I have the inner product of that with UR tilde, the inner product becomes 0. Because inner product of two orthogonal vectors becomes 0. So this term goes away completely, becomes 0, scalar, right? And I have the rest. Okay. Now, this lambda L, I can drop it because I can divide the sides by lambda L. 0 over lambda L becomes 0. So this goes away. And I have UR tilde transpose this term here and also UL tilde equals 0, right? Now consider this middle term, TR outer product RR. According to, I just don't prove that. I'm just referring you to some book. According to the problem 16.2 in the textbook reference 5, this outer product, you can write it as this matrix multiplication, ATR RR, where ATR is the antisymmetric matrix of TR. It's this. Okay, so and RR is the same as this rotation matrix. Okay, now as a result, I can replace this outer product with equation 63. It becomes equation 65. This becomes this. I'm repeating it here. Now, this term, I define it to be essential matrix. It's denoted by E. Okay, this TR outer product RR also equals ATRRR. It's a 3x3 matrix, and it's denoted by E in the literature of computer vision. It's called essential matrix. So I can replace this by E. Therefore, I will have this. You see, the proof, which will not be in your exam, you know that. The proof was complicated, but the result was very simple. Very simple. So what is this? This is one of the most famous equations in computer vision. UR tilde transpose E UL tilde equals 0. And 0 is a vector, scalar. Why? Because this is a 3x1 vector, right? Because we have 2 coordinates in the pixel, but it's homogeneous. So it's 3x1. This is 1x3, and this is 3x3. So the whole thing is one equation. The whole thing is one equation equals 0, right? And what is it doing? It's just basically mapping the points of the left camera to the pixels of the left image to the pixels of the right image, or the other way around. So it's just a translation between the pixels of the two cameras, right? But here, we assume that the cameras are normalized, as done in equation 59. Now let's relax this assumption. Now let's surpass the assumption of normalization of cameras. Let the two cameras be any general cameras, and their intrinsic matrices characteristics might be different. Again, suppose that the left camera is on the origin of the 3D space, which is it's my choice, right? Without any rotation. So again, right rotation matrix is identity, and left rotation matrix is identity, and left translation vector is 0. Now consider that famous equation of mapping. Now I can't replace KL with identity. The rest is as before. Okay, this 0 multiplied 1 becomes 0, goes away, and I will have K, and this KL is also a pain in the neck. Left multiply the sides by KL inverse. So I will have KL inverse lambda, this is this, equals this, but without the last thing, because this is multiplied by 0. Now consider the right camera, the famous mapping equation for the right camera. Again, I can't replace KR with identity now. What happens? Here, I have x, y, z. I replace it with equation 68. And equation 68 is this, right? Let's continue. So this is what we had. Okay. Now I have, this is my homogeneous UR tilde. What about the rest of the terms? We know that KR, TR is multiplied by 1. So I have, So I have plus KR, TR. Also, I know that KR, RR is multiplied by this. So it becomes like this. And you know that this part is just UL tilde here, right? Now let's simplify this. This KR is a pain in the neck. Left multiply the sides by KR minus KR inverse transpose, right? So if I do that, this goes away, and I will have this KR inverse transpose. And this went away, right? And also this KR goes away. So these two KRs go away. Now what happens? Now I left multiply the sides by TR outer product as before, as we did before. Why? Basically to get rid of this term, because TR outer product TR becomes 0. Then I know that lambda R is a scalar, so I can bring it out. Also lambda L is a scalar, I can bring it out, and the rest is as before. Then what do we do? Then I left multiply the sides by KR minus transpose, KR inverse transpose again. Sorry, KR inverse the previous, yes, again. So I will have this, and yes. So this term is here. Also this term is here. I have left multiply the sides by KR inverse transpose. Then what do I do? Then again, left multiply the sides by UR tilde transpose. So I will have this. Why do I do that? To get rid of this term. Because I know that this term is this term. Is the outer product of something with UR tilde. Therefore, it's perpendicular to UR tilde. Therefore, its inner product with the UR tilde is 0. So it becomes 0. And the rest is as before. Okay. Now, lambda L can go away because I can divide the sides by lambda L. 0 by lambda L becomes 0. And this is the rest. So this is a term in between. Right? So we have this. And as you see, in the previous time, we didn't have these two terms. Now these two terms have been added. This we had it before, right? We denoted that by E, essential matrix. Now, this time we have these two. So I'm repeating it here. Now let's define this to be fundamental matrix, F. This is a very important matrix in computer vision. This is KR inverse transpose, essential matrix, KL inverse. This is 3 by 3. This is 3 by 3. This is also 3 by 3. So fundamental matrix is also 3 by 3. Okay. You can also reset it to be this. Why? Let's prove that. So right multiply the size by KL. So we'll have FKL equals KR inverse transpose E KL inverse KL. This becomes identity matrix. Also, this is a pain in the neck. Left multiply the sides by KR transpose. So we'll have KR transpose FKL equals KR transpose KR minus inverse transpose E. This is also identity. We get this equation. Okay. So if we replace this with fundamental matrix, we get this. This is also one of the very important. I think this is the most important equation in computer vision. What does it do? This equation maps the points from one image to another image. As you see, the result is simple. So these are the pixels in one image, left camera. These are the pixels in the right camera. You see that? And also this is a one equation because this is 3 by 1, this is 1 by 3, and this is 3 by 3. We can find the parameters of the fundamental matrix. We need to find that, right? Using pairs of corresponding pixels in the two images. Consider ULI tilde and URI tilde. What do I mean? We have several pairs. They are the ith pair in the left and right images. Okay. For the ith pair, I can put the ith pair in this equation 75 to have this. It's just one equation, right? It becomes one equation. So it gives me one equation. How many unknowns do I have? It's a 3 by 3 matrix. So I have 9 unknowns. And 9. So we might need 9 pairs. However, it can be shown that the degree of freedom of the fundamental matrix, I just don't prove that, see the reference 5, is 7. So if we find only 7 parameters, that's enough. For 8, I can tell you why. But for 7, I need to see the proof. I don't know it yet myself. So when you have 9, for example, unknowns, you can assume that one of them is fixed and find the 8 other ones up to scale, right? Up to, because when you change the scale of the one of them, then the other ones will be changed. So up to scale, 8 of them is enough, are enough. However, according to some proof, maybe 2 of them are redundant. So 7 are enough. As a result, we need 7 pairs, and 7 pairs are sufficient to find the fundamental, uh, the values of the fundamental matrix. And we can use Cramer's rule, right? Just acknowledgement, some slides of this slide deck are inspired by chapters 14, 15, and 16 in this textbook, the Simon J.D. Prince, Computer Vision Models, Learning, and Inference in 2012. So basically, we covered 3 chapters of this textbook. And this is a very important textbook. And also some slides of this slide deck are inspired by teachings of Professor Hoda Mohammadzadeh at Sharif University of Technology, Department of Electrical Engineering in Iran. Our teachings were based on Prince's textbook. Okay. And these are the references. So what are these? These KKT conditions, first order, second order optimization, and distributed optimization tutorial and survey. This is our tutorial paper about optimization. I recommend that you read that. I think it's very good. Also, I have a course, optimization techniques, in my YouTube channel, and I cover various methods in optimization. Also, this high accuracy stereo depth maps using structured light. This is exactly the technique that I told you that they use to improve the time complexity of finding the depth of all points in the scene. The Haar wavelet transform, it's about the Haar wavelet transformation. This one is about the Viola Jones face detection, which uses Haar wavelets, remember. And this is Prince's book, published in Cambridge University Press. Okay. Any question? Was it clear? Yes.
Thank you so much. Is it possible to put your email address in the chat to re-ask
Yes.
questions? Yeah.
I will be at. I have several emails. My Guelph email is UO. Yes. I'll also put it on the chat. Okay. Any question? Any
Thank you
other
so much.
question? No problem. So B Kojok. B is start Benjamin, and Kojok is my family name. Any question? No, everything is clear. Okay, great. So let me stop sharing. How can I stop sharing? Yes. Okay, let me stop recording.